The other interesting function is the impulse function, or Dirac impulse function. This function is telling the story that this function doesn't have much value, doesn't do much at other time. It only do something at a specific time. And it does actually tremendous amount of efforts at this specific time. It's a large impulse over here. This is actually not a regular function. It's a generalized function, or sometimes called a distribution. This similarly simple function actually is very interesting to study. The motivation is as follows. We have learned that when dealing with ordinary differential equations, we have differentiation, right? We need to calculate derivatives. Now, even for a simple function that look like this, a simple system that look like this, y dot minus ay equal to u dot plus bu, even for this simple first order dynamic system, something interesting will happen if we supply a step signal as an input. Why? A step signal looks like this. It doesn't do much, and then it jumps to have a value of 1 as a step. So the step function, everything else here is okay, we know the value, and the value doesn't change. But the step function, a lot actually happens at the origin, or when it jumps. So when it jumps, it's not continuous anymore. This step function is not a fully continuous function. It is a piecewise continuous function. Now, when you have that, think about what may happen when you consider derivative at this point. Okay? The derivative at this point, you cannot write it up as a common function that you see at other places. So, in sum, if u is a unit step, 1 of t, u dot will have a jump at 0. And then we don't have a way now, at least for now, we don't have a way to write this big jump at 0. So we cannot directly evaluate u dot in this case. And then we don't have good intuition. If we can't evaluate u dot, then we don't have good intuition about this solution of the system over here. So we must do something, in other words. Now, if you think about the problem, what's the origin of the problem? The problem is when the step signal jumps, we cannot evaluate the derivative very easily. However, we can approximate a step like this. I define another function. It looks like a step when time is large enough. And it's also 0 when t is negative. So I have these two areas checked. And then in between, remember, we have a big jump. We cannot evaluate derivatives very easily. It's not continuous. I can do this. I can use this to approximate. We can have a slope between 0 and 1 to approximate. And the slope is defined by this variable epsilon, which is the value over here. I can change the epsilon. This is a perfectly continuous function, right? It's not discontinuous at all. I can change epsilon by reducing epsilon slowly to 0. I can approximate a step function like this. So when epsilon is very tiny, when I let epsilon to approximate 0, then I can have a very close representation of the step that we have originally. Okay, the benefit of this approximation is that this new signal, this approximate of the step function, I can have derivatives very easily. Its derivative in here is 0. Its derivative in here is also 0. And in between 0 and epsilon, what's the derivative? It's a constant slope. So the derivative is a constant. And then if you do the calculation, it's actually 1 over epsilon. So this one, we can calculate the derivative very easily. In other words, we have no problem in the original example, y dot minus ay equal to u dot plus bu. No problem. We know everything in this input side, on this input side. So we can change the epsilon again to make the function to be more closely representing the step function and its derivative. So reducing epsilon, we can gradually go back to the step function. As you reduce epsilon, you can see the slope increases. In other words, the derivative will also, the value will also be bigger between 0 and epsilon. So we can keep doing this, reduce epsilon, and then finally get something really, really sharp at 0 with a very, very large magnitude. So that's how the concept of an impulse appears. The benefit, now we know we can calculate the derivative. It also has a few nice properties. First of all, if you integrate this impulse function over the time, then this is nothing but the area, right, underneath the rectangles over here. The height is 1 over epsilon, and the width is epsilon. So the overall area is 1. It's 1 over epsilon times 1. Okay? So you integrate the impulse, you get 1, which is the value of the step function. And then if you do a integration of f, if you do integration ft times this impulse, ft times this mu epsilon dot function, then you can see nothing happens when t is less than 0. Nothing happens when t is larger than this epsilon. So this integration, although it's from negative infinity to infinity, is actually only matters when it's from the time is from 0 to epsilon, right? And when time is from 0 to epsilon, this function, this approximate impulse is a constant, 1 over epsilon. So, what do you know about this evaluation over here? If you take the limit and you integrate ft divided by epsilon, and the integration region is from 0 to epsilon, what is that number? This is essentially, if you have a function, you break it into, this is essentially discretization. You can approximate a function by this small chunks of discretization. So when you look at here, between 0 and epsilon, if epsilon is small enough, then f will be approximately the value of f0 in this region. So therefore, this evaluation is actually f0 over epsilon approximately, and then epsilon minus 0. F is approximately a constant in this small, very tiny, tiny region. So it equals to f0. So if you multiply impulse to a function, then you integrate it, it gets the value of that function. at that specific impulse time. So these are some of the properties of the impulse. This generalizes. So if you keep doing this and epsilon approximates to 0, then we can have this generalized function, the impulse like this. And then you can have the impulse to be not strictly at 0 as well. You can apply the impulse at other time, t, capital T as well. Then the properties will still remain. If you integrate any impulse, it will integrate into 1. And if you can get integration of impulse times a function, then it picks the value of that function at this impulse time. Those are the properties of the impulse. There are still some, if you think about the problem more carefully, there's still a few things that can cause troubles. This impulse, the way that we construct it, it's a rectangle shape, so it has value, it's continuous, no problem, outside of this box. And then inside this box is also continuous. But it's only piecewise continuous, right? It still needs to jump at time 0 and time epsilon for this impulse. So that means you cannot do differentiation to this impulse on the left-hand side. This one is not well defined when you have the jumps. So this approximation of the impulse is not the ultimate form. It's advantageous, but it's not the ultimate form that we want to have. Because in practice, we may see something like this. On the right-hand side, we can have first-order derivative of the input. I can also have third-order, fourth-order, etc. Right? Now, for this one, what we have taken care of is the first-order derivative, right? The first-order derivative of this approximate step is like this. But I cannot go further down the differentiation path. So what can we do then? We can apply essentially the same technique. This is not differentiable, right? But we can do something like this. I can approximate the impulse using not a rectangle. I can approximate the impulse like this. It's still 0 when time is sufficiently large, and it's 0 otherwise. And inside this region, it does this approximation of the impulse. More specifically, mathematically, it increases when t is from 0 to epsilon, increases like this, and then decreases back to 0. Compared to this impulse function, this one is now continuous. It's piecewise continuous, right? It has derivative here, it has derivative here, it has derivative here. So that means we can evaluate another order, another level of derivative now. And we can change the epsilon value to make it more like an impulse. We can reduce epsilon so that this peak is more sharp. It's sharper, sharper, and then it looks like an impulse in the end. Okay? So this approximation of the impulse not only is more differentiable, but if you integrate it, is actually a smoother approximation. If you just do a rectangle type of impulse, then the slope is constant in this region. Now it's a smoother approximation. Okay? This smoother approximation of the unit step is more differentiable than the previous one. By construction, in this way, is actually twice differentiable. And we can make this impulse shape to be even more smoother. We keep on doing things like this. then we will have actually possible to have an infinitely differentiable impulse function. That is the power of the distribution or generalized functions. This generalized function, impulse function, is infinitely differentiable. If you want to know more, we can apply this concept actually to rigorous research. So we have some publications along this. It turns out this kind of jumping, if you look at the jumping behavior carefully in a control system, it can mean a lot for certain classes of motion controls. You can see here, in a nutshell, if we take into account these jumps and we use this impulse, this generalized function, to model them more accurately, then we can reduce from the red line to the black line over here. We can control this discontinuity very efficiently. So that is some application of the concept. You can read more going to this paper link on the screen over here. Any questions about the impulse?